In this section, we talk about an idea called electronegativity, which is really just an acknowledgement that not all types of atoms are identical. When we looked at the hydrogen molecule earlier, we said that bonding occurs when the electrons are positioned exactly halfway between each nucleus. In this arrangement, the major attractive force is the inwards attraction of the protons towards the shared electrons. The reason that these electrons in this molecule sit exactly halfway between the two atoms is because the two atoms themselves are identical. However, most of the time, most bonds don't involve identical atoms, but rather involve different types of atoms. And what will happen is that the electrons are not shared equally and will sit closer to one atom than another. So, for example, in the hydrogen chloride molecule, the electrons sit a lot closer to the chlorine than they do to the hydrogen. That is, that the chlorine gets a greater share of the electrons than the hydrogen does. To indicate this, we can use either what we call a polar arrow, which is an arrow pointing towards the end of the bond that gets the greater share of the electrons. We turn it into a polar arrow by making the other end of the arrow into a plus sign. Another way that we can indicate that there is an uneven sharing of electron is by using this delta notation, where the end of the bond that has less electrons is labelled as delta positive, and the end of the bond that has more electrons is labelled as delta negative. When we have a bond where there is an uneven sharing of electrons, it's often referred to as a polar bond. And it's also worth noting that we're going to use the language a little bit that any object, whether it is a bond or a molecule, etc., that has a slightly more positive end and a slightly more negative end, it's got two poles to it, that is referred to as a dipole. So if you hear people saying that the bond has a dipole, that is, it has a positive end or a negative end, and a negative end, or you hear people talking about a polar bond, they're talking about the same thing. There's two ways of indicating that you have a polar bond. You can use a polar arrow, where the arrow is pointed towards the end of the bond that has the greatest share of electrons, and the other end of the arrow is turned into a plus sign. Or alternatively, you can use the delta notation, where you label each end of the bond as being either delta plus or delta minus. As electrons are negative, the end of the bond that gets the greatest share of electrons is labeled as delta minus. To draw the delta symbol, I normally write an S and then just close the bottom loop. So you can predict what pairs of atoms will form polar covalent bonds without even sharing of electrons using the periodic table. Effectively, the tendency to pull electrons towards itself increases for an atom from the bottom left to the top right towards fluorine. Now, there have been a bunch of schemes that are intended to give a quantitative number to this quality that we call electronegativity, that is the tendency of an atom to pull electron towards itself in a polar covalent bond. So the higher an atom's electronegativity, that greater tendency to pull electrons towards itself. Perhaps the most famous and widely used electronegativity scale is that developed by Linus Pauling. Linus Pauling is a very famous American chemist. He actually comes from the Pacific Northwest, from Oregon. He won 2 Nobel Prizes in 2 different disciplines independently. So he did it all by himself. Often the Nobel Prize is awarded to a group of people. And he's kind of an interesting guy. It turns out that he never actually did officially graduate high school, and that's because he was, killing it in all of his math and chemistry and physics classes, and he was allowed to move on to the university before he'd actually completed his humanities requirement. And if I remember correctly, the myth is that he pulled the same stunt at the university, and he actually was allowed to graduate from his bachelor's degree and enter his graduate program without actually finishing off all of his requirements. Now, electronegativity again increases this way, and the most electronegative element on the periodic table is fluorine, with a value for electronegativity of 4. So this is what it looks like, and you can see that the nonmetals over here they all have high values for their electronegativity. As I said, fluorine has the highest value of 4. And then the metals, they all have very low values for their electronegativity, in some cases being even less than 1. So that's generally how it works. So if we're given two atoms, and we know, say, like hydrogen is one of the least electronegative non-metals, and then say pairing that up with nitrogen, so in a hydrogen to nitrogen bond, we know that the electrons are going to lie much closer to nitrogen than they do to hydrogen because of the differences in electronegativity of those two atoms. You can see there's a difference here. Nitrogen is 3, hydrogen is that. There's at 2.1, there's a difference of 0.9. So electronegativity is the tendency of an atom to pull electrons towards itself in a covalent bond. Electronegativity increases from the bottom left corner of the periodic table towards the top right corner of the periodic table. So we talked a little bit about this already, bond polarity. When we have an unequal sharing of electrons, our bond will be polar. The question is when is this important? Some bonds might be more polar than others. So when atoms with different electronegativity share electrons, the electrons are not shared equally. As we pointed out in hydrogen chloride, the chlorine atom will get the much greater share of electrons than the hydrogen atom. The bond is said to have a more positive and a more negative end. That is, it has a dipole, and we can indicate that using either the delta notation or the polar arrow. So when does it become important, and how can we classify bonds? Well, generally we're going to say that if the difference in electronegativity between two atoms is between 0 and 0.4, that we have almost equal sharing of electrons, and we won't really see any big impact on that particular bond's chemical properties as a result of this nearly equal sharing of electrons. So we're going to classify bonds that have differences in electronegativity of between 0 and 0.4 as being nonpolar covalent. Now, if your difference in electronegativity is greater than 0.4, then that's going to result in significantly unequal sharing of electrons, and we're going to classify the bond as polar covalent, and we'll see obvious manifestations of this in the molecule's chemical and physical properties. So that's, this is our kind of a cutoff here. If the difference is greater than 0.4, then it's going to be classified as a polar covalent bond, and that will manifest with giving the molecule particular types of properties that we wouldn't otherwise see. Now, once you get really big differences in electronegativity, so we're talking about greater than 1.5 here, this is typically what we're going to see for ionic bonding. We don't really have sharing of electrons anymore. The electrons have been completely pulled over to one atom. You might see the occasional sort of molecule, perhaps with hydrogen, that has a difference like 1.5 or higher. So hydrogen with fluorine is 4, hydrogen was 2.1, I believe, and so that's going to give you a difference, of 1.9. So that's a very, very, very polar covalent bond. Beyond 2, the electrons are not shared at all. There's no possibility for that. That's just an ionic bond. Okay, so our cutoff really is if the difference in electronegativity is greater than 0.4, then we're looking at a polar covalent bond. So the sharing of electrons between atoms with different electronegativity will give rise to a polar bond. And what we're going to say is that if that difference in electronegativity is greater than 0.4, then the bond will be significantly polar, and that will have an impact on the properties of our molecule. Now, once we get beyond a difference in electronegativity of about 1.5, then it starts becoming extremely polar, and even this is we may even see complete transfer of electrons. Once we move beyond a difference in electronegativity of 2.0, then we don't have sharing of electrons at all. We just have complete transfer of electrons to the more electronegative element. So, related to bond polarity is molecular polarity. And molecular polarity is a little different. The presence of polar bonds doesn't mean that our molecule will have a polar and a positive and negative end. So I'll give you a little example of this. If I look at carbon dioxide, if I consult a table, or I can just look at the periodic table, electronegativity increases that way, and we can go carbon, nitrogen, oxygen. I would see that oxygen is more electronegative than carbon, like that. If I use my delta notation, I would label each of the oxygens as being a little bit negative and the carbon as being a little bit positive. And you can see that there isn't a positive end of this molecule and a negative end of this molecule, right? There's regions where, some parts are more positive than others and some parts are more negative than others, but there's not a clearly defined positive and negative end. This molecule is not polar because it doesn't have a dipole. There's no dipole there, right? There's not a more positive end and a more negative end. So I guess what I'm really getting at is that the presence of polar bonds doesn't mean that our molecule will be polar. It might mean our molecule polar, but it doesn't automatically mean our molecule is polar. So molecules can have a polarity. That is, they can have a positive end and a negative end. And that will happen when we have an unsymmetric distribution of electronic charge about the central atom. So water molecules are polar because they have two polar bonds, one going up and to the right and one going up and to the left. And the overall result of that is that the oxygen end of a water molecule is slightly negative, and the end of the water molecule where the hydrogen atoms are is slightly positive. So you see there's this kind of negative end, and then there's this positive end. And so that's, that gives rise to an overall positive and negative end of the molecule. The molecule is polar. Now, if water molecules weren't bent, we would be in a similar scenario as what we were with the carbon dioxide, where we would have alternating regions of electrical charge, but it doesn't have a net positive end and a net negative end. There's no way. It doesn't have a dipole. It's not polar. Now, the fact that water molecules are polar is really, really interesting because it means they attract one another. And you've probably seen this, water tends to bead. What happens is that the positive end of one water molecule will be attracted to the negative end of another water molecule, and so on, and a network of these interactions will form throughout a sample of water. So this is called a dipole-dipole interaction because the dipole on one water molecule is interacting with the dipole on another. And the dipole-dipole interaction in water is a particularly strong example, and it's often referred to as a hydrogen bond. And these things are extremely important in biochemistry. It's what gives proteins their shapes so that they can fold and have particular shapes and perform particular functions. And it's also what gives rise to the DNA double helix. So basically, you wouldn't be alive if it wasn't for the fact that the positive and negative ends of different molecules attract one another. So in general, if we have an even distribution of electron groups around our central atom, the molecule will be non-polar. And the example that I gave before of carbon dioxide illustrates this nicely. This central carbon atom has two identical things attached to it. It's completely symmetrical about that carbon atom, and as a result, it's going to be non-polar. So you don't necessarily need to think about how these polar arrows add together to determine whether a molecule is polar or not. If it has identical things on the central atom, it's going to be nonpolar. Okay, so when I look at this methane molecule here, drawing it in 3 dimensions, it's tetrahedral. All 4 things attached to that central atom are identical. They're all singly bonded hydrogens. So without really even thinking about the polar arrows, I automatically know that this guy is going to be nonpolar. Now, if I do draw the arrows in and think about it, they will all cancel out and there isn't a net positive or negative end to this molecule. The hydrogens will all be a little bit positive. They're all going to be on the outside. The carbon in the middle there is a little bit negative. There's no one end of this molecule that is positive and one end of the molecule that is negative. However, if we have an uneven distribution of electron groups around a central atom, our molecule will be polar. So what I mean here is more than one thing on the central atom. That's going to give it that asymmetry. So for water, it has 2 identical singly bound hydrogens on the central atom, but it also has 2 lone pairs. So I don't necessarily need to think about where the charges are or to use polar arrows. Just the fact that I've got these 2 different things on my central oxygen atoms automatically makes that polar. I can decide that on the basis of the Lewis diagram. If I go to look at this ammonia molecule here, I could look at how all these arrows are all pointing up towards the nitrogen, which would indicate that that end of the molecule was a little bit negative and the base of the molecule was a little bit positive. But I could also recognize that there's 2 different types of things attached to the central atom here. There's a lone pair, and then there's these 3 singly bonded hydrogen atoms. So again, because of that asymmetry about the central atom, that would be automatically classified as polar. So if we have an asymmetrical distribution of electron groups about the central atom in a molecule, then that's going to give us a polar molecule. You can easily recognize whether a molecule is polar or not because polar molecules always have more than one type of thing, i.e. more than one kind of atom or atoms and lone pairs attached to the central atom.